we're starting off the architecture topic with Ben. Then we're going to jump back to cognition for a moment with Peter. But Ben Goertzel, Dr. Ben Goertzel, on bridging AGI theory and practice with Galois connections.
Yeah, so this is a 15-minute talk on a larger than 15-minute topic, and it's also a topic I talked about already in 2021 in the previous AGI conference, but I didn't submit a paper. So this year basically, so there's a long paper on ArcSci for those who are interested, which is called The General Theory of General Intelligence. I was in an even more immodest than usual mood then, and basically that tries to take you all the way through a sort of intellectual adventure from like, what is intelligence, what is awareness, what is life, the universe, and everything, and take you through cognitive science and some philosophy of mind, all the way to why are we doing what we're doing with OpenCog Hyperon. Now I recorded like 6 hours of talks on YouTube, like walking through that whole paper, and there was I gave a compressed version of that deck at AGI 2021 in a talk. So I mean, if your curiosity is piqued by what I'm going to race through in 10 minutes or so here, then you should look at that. I would say the talk I'm going to give now is based on a paper I submitted for the proceedings this year, which is some little segment of, it's a blown up version of a little segment of the General Theory of General Intelligence paper, and will make most sense to people who have already seen the relevant bits of mathematics before, because there's just not time to really explain like what is a Galois connection and why in this length of talk. So now let me jump into some slides here. Okay, we'll start here. Okay, but that is not good. Why is that so big? All right, give me a moment to fix my PDF view. Oh, there we go. Okay, that's gonna do. So the particular bit of applied math I'm gonna go over here. It was born of the desire to take a wide variety of algorithms that I think are useful for building AGI systems and cast those algorithms in a very common mathematical framework, not just because it's a sort of elegant thing to do, because I wanted to be sure that our new version of OpenCog, the OpenCog Hyperon system, could do all these things efficiently. So if, we could try to make it do probabilistic logic reasoning, evolutionary program learning, attention allocation, probabilistic programming fast. But it seemed like, okay, why not instead try to cast all these in some common form, so then we could just make that common thing fast inside the interpreter for the language called Meta, M-E-T-T-A, Meta Type Talk that we built for the system. So I started by basically trying to represent all the AI algorithms that we want to use in our AGI system as approximate stochastic dynamic programming, which if you think about it, they kind of all are. I mean, reinforcement learning originated as approximating like Bellman equation from dynamic programming. And so I formalized that as something called a discrete decision system, which is just a system making an iterated series of decisions based on trying to minimize some cost or maximize some reward. And each decision it makes affects the state. So that's a very general and not very original way of looking at things. And in the paper, I go over how to portray various cognitive processes in these terms, such as spreading activation or function optimization. So I introduced what I call combinatory operation-based function optimization, which is a fancy name for something really simple. Like you have a bunch of guesses at things that might optimize a function. You combine them with each other by some combinatory operations. you pick the best combinations by some heuristic, you see how they will do it and on the objective function. You take that data and feed it back in to guide the making of new combinations. So you have sort of a cycle of combining your guesses by some operations, filtering them, evaluating them, using the results of the evaluation to help with the combination and filtering. And this sort of process is also a discrete decision system, right? I mean, this sort of process also pretty much can be cast as approximate stochastic dynamic programming if you want. And you can write that in pseudocode, which I did in the paper. You can also view it in an abstract way as a sort of probabilistic programming, because what you're doing, you have a bunch of combinations of earlier guesses and you're sampling from them from some distribution. And then you're taking the ones that you drew from that distribution and you're evaluating them in the function, getting new data, using that new data to guide the sampling your next time around. Then you can then make this recursive in an interesting way, wherein the algorithm that you use to guide the sampling based on the data could itself be another discrete decision system, right? So then you have, but there's a long lineage of learning probabilistic programs that learn probabilistic programs that learn probabilistic programs. I mean, so that many of these things have been seen before in particular domains. Now, what we're doing in the OpenCog system that we had a whole workshop on yesterday, which you could see the proceedings of on YouTube if you're interested. We're building an AGI system where the central architectural component is this large knowledge metagraph, which is a sort of souped up version of a graph with like a hypergraph plus links to links, links that point to multiple things, links that point to subgraphs and so forth. And so the model we're using there, we're trying to view the cognitive processes underlying AGI as hunks of a metagraph, which are then interpreted as transformations that take part of a metagraph into another part of the metagraph. And these particular metagraph encoded programs for metagraph transformation were in many cases interpreting these as combinatory operation guided function optimization, which can be arranged in this sort of discrete decision process, which is approximate stochastic dynamic programming. And so this leads into a line of thinking regarding metagraphs. You can look at untyped metagraphs, undirected metagraphs, directed typed metagraphs, and there's a connection here with germs and sheaf theory and stuff, which I won't go into. But you can also look at paths through metagraphs, which is sort of like a path through a graph, except your edges are snaking around and pointing to many different things. You can construct these mathematically using initial algebras and build up these metagraphs bit by bit from a bunch of different constructors. And you can look at different sorts of initial algebras, like different sets of basic combinatory operations. You can look at the topology on these metagraphs, which has to do with Hating algebras, which is a similar algebra used inside intuitionistic logic. And this leads us to some practical functional programming-y stuff, which has been important in designing the OpenCog Hyperon system. So one sort of operation that's often useful to do when implementing complex algorithms using functional programming is fold and unfold. And if you've done programming in Haskell or Camel or something, you've seen folding over lists. Then you can also fold over trees. Here we're folding over metagraphs. And there are other weird sorts of folds where you can fold through a data structure and carry memory through as you fold. And these have a bunch of unnecessarily weird sounding names, like histomorphism that counts a history, or futuremorphism where you're unfolding and so forth. And you can look up the members of this sort of morphism zoo. But one conclusion I came to is that most of the algorithms I wanted for AGI, I could implement as folding or unfolding over a metagraph. In particular, the fold and unfolds that carried memory, like the histomorphisms and futuremorphisms. So I came to the conclusion, within a rough degree of approximation, if I could make histomorphism and futuremorphism over a metagraph fast, then I could probably make a lot of the algorithms I need for AGI fast, which posed me the technical problem, like how to make an interpreter or compiler to make these operations fast, which led to a bunch of the stuff we discussed yesterday about compiling our metagraph language into Greg Meredith's row calculus and his efficient row calculus compiler for concurrent processing and so on. But what I'm talking about here is sort of mathematical reduction that led me to think, if I could do this sort of folding fast, then that lets me do a lot of the stuff I want to do inside an AI architecture fast. And so I go through some work to formalize these sorts of morphisms on directed type metagraphs, which it's a special case of a bunch of category theory, but it hadn't been articulated for this case before anywhere I could find, and that's too much to go through in a brief talk. There's all these ugly kinds of morphisms, but the bit of this that I wrapped up in the paper in the proceedings had to do with Galois connections, it's a particular sort of adjunction if you look at it in categorical context, but there's a literature specifically applying Galois connections to certain sorts of algorithms in a functional programming context. And if basically a Galois connection, it's a pair of adjoint functions just mapping one partial order into another in a nice way, which you can see from that equation there. I mean, the pointy less than the square less than are two different partial orders, and you're moving f on one side to g on the other, and the connection is between the f and g. And there's a literature in the functional programming world that uses this to find nice ways to do things. So like the standard Euclidean algorithm for doing long division, as a classic example, like you can derive that this way by the Galois connection between multiplication and division. And so this is used in functional programming to do sorts of automated programming. Like, can you automatically derive the Euclidean algorithm for division? Well, you can if you just know how to do multiplication in the simple way, and then you set up this Galois connection. You can automatically get the standard algorithm for division. And so this hasn't had that big a practical use in the functional programming world, but it's one of these things that always seems like it should soon have a really big practical use, and it's quite cool. And I would say, these fold and unfold were the same way as was category theory. When I was in grad school, they weren't that useful. It seemed like they would become that way. Now they're super useful in functional programming land. So I realized this combinatory operation-driven function optimization, you could use Galois connections to formalize this and figure out nice ways to represent the sort of iterated combination and function evaluation scheme to implement that in terms of fold operations. So greedy optimization was the first case to look at, and a lot of AI algorithms in practice are based in greedy optimization in some form or another. And evolutionary learning you can view as a sort of greedy optimization on the space of populations, actually, and hill climbing, steepest descent. All these things are in the end a sort of greedy optimization. And you can express greedy optimization as folding. And this is a theorem in the paper, but it comes pretty, and the notation is forbidding enough. I'm not going to try to explain it in 1 minute. You have to look at the paper, but it falls fairly directly from previous results in functional programming literature. So if you have a greedy optimization algorithm over a metagraph, you can use the Galois connection to reorganize that into folding a certain operation over all the nodes and links in the metagraph. And so this gives you a way to turn it into a sort of nice iterative thing. Now, the next step there is to use Greg Meredith's row calculus to take this fold over the metagraph and do it concurrent processing over all the processors in the GPU. But you can do that because you've written it as future morphism and histomorphism, which is nice and elegant functional operation. But you can also represent dynamic programming as a Galois connection, and including the approximate stochastic dynamic programming. And that gets you further toward reinforcement learning, probabilistic programming, various sorts of inference control. There come out to be some interesting math things there. So if you're combining guesses and then sampling from the combinations and evaluating them and taking the evaluations to guide your sampling, that works if your combining operation is associative and you can make all the Galois connection stuff work. If you're combining guesses in a non-associative way, then you can't munge the parentheses around and you don't get a Galois connection route to representing dynamic programming as fancy folding. So you do, and this sort of finding was actually a relief to me, because if things are too easy, you get the feeling it's trivial. Like you want there to be some restriction on what operation can work. So it seemed that the same math of Galois connections you can use to connect times with divides and then figure out Euclidean algorithm for division. Seems like you can use that same math to take greedy algorithms, dynamic programming algorithms, and rearrange them into folds over the metagraph. And then that's nice in terms of guiding language design for AGI, because it means if you have a language interpreter and compiler that can do these fancy folds over metagraphs in a fast way, then maybe you can do your AGI algorithms in a fast way. And there's some caveats here which are ugly and we haven't fully worked around. And that's always the case in building real AI systems, because of course there's a question when you're folding over this graph, are you modifying the graph as you fold? Like if you're modifying the graph as you fold, then all the theory doesn't hold exactly, right? No, you don't have to modify the graph as you fold, but it's sort of the cognitively natural thing to do, right? So if you do modify the graph as you fold over it, then you have like approximate versions of all these theorems that I didn't bother to work out yet. But I was sort of heartened that so much of this worked, and we're using this not so much to figure out the cognitive parts of the AGI design, but we're using it to figure out how to make an efficient implementation for the AGI design. But this does tie back to sort of the broader themes we're seeing in this event, right? Like I was teaching neural nets in the 90s. Recurrent backprop on a 30 neuron network took like 3 hours on the servers I had when I was a professor then. So now we've got massive scale behind transformer neural nets, which they're not recurrent. You got attention replacing some recursion, but they're not that recurrent. But just adding all this scale allowed these networks to do some quite amazing things, even with some little bits and pieces of emergence here and there. So the open question that's in everyone's mind is, okay, well, what if we take all these other cool algos from the history of AI, like, say, logic theorem proving or evolutionary learning? What if we take these other algorithms and we jack up the scale tremendously also, right? I mean, then what happens? Do we get more magic emergence? What if we connect those all together, right? So the infrastructure is different though, because these aren't just matrix multiplication, right? Or not in the simplest, most natural way. So what we've been trying to do is figure out how to take logic, evolutionary learning, certain types of probabilistic programming, take these things and build an infrastructure that will let you do them super fast. That becomes harder because these are graph-based. It's harder because they're not sort of map-reduce oriented. You need things like row calculus, which is fancier to make them efficiently concurrent processable. But it seems to be doable given current compute hardware and current state of computer science theory. So if you want to dig further into this stuff, you can look at the videos from the OpenCog Hyperon workshop yesterday, or the videos or the full paper on general theory of general intelligence, and it goes through all of this. This was sort of the abstract to the abstract, but if you're mathy enough, it may whet your appetite. Thanks a lot.
Thanks very much, Ben. Do we have any questions for Ben in the audience? Thank you, Noah.
So I like massive hylomorphisms as much as the next nerd does. But that's only one of the directions of scaling, right? The other direction of scaling that's turned out to be important is the amount of data.
Yeah.
Can you say something about like how do you get a massive amount of data into a system?
Yeah, I would say amount of data can be measured in various ways also. So like in an applied context, we're working on problems in genomics where you have like 15 populations and massive gene expression and mutation data. So that's a big body of data, but there's a small number of examples. And we found this sort of system is much better than current neural networks at dealing with data that's like small in one dimension, but massive in the other dimension. But in concrete sense, there's two ways we're working to get massive data in here. One is, as will be talked about by Andres Suarez and Manhin in the workshop tomorrow. I mean, we're using LLMs to translate the web into higher order logic form and then feed it into this metagraph. So, I mean, the thing is, we just need to massively scale up our system to handle all that. So, like, we're starting with Wikipedia, which used to be considered big, but now is trivially small. The other thing is, I mean, we're working with humanoid robots. We've been working with Hanson Robotics, with the Sophia robot, and other humanoid robots for a long time. So, I mean, we're feeding in auditory, a limited amount of haptic, a lot of visual data from these robots. So far, we've been using sort of standard deep neural nets using Torch, and then having a symbolic network that connects into the Torch compute graph, right? So we haven't been trying to do the perception in the symbolic network. We're doing perception neural net and then getting neural symbolic. So I do think the data requirements for this sort of system, in principle, are probably significantly lower than with the transformer, but because it is trying harder to abstract, but they're still going to be large, and exactly how large they'll be is going to be empirically discovered.
Ben, thank you for the talk. What you can say about the hardware, where we are at in terms of
well, this is
efficient
a beautiful chance to advertise for the AGI hardware workshop tomorrow, where I will, among other things, I will present a new chip design I've come up with, which does metagraph pattern matching on the chip. And then Rachel St. Clair who's maybe somewhere here, no, she's hiding, but Rachel St. Clair will present her chip for hypervector manipulation. And one of the things I didn't talk about here, but we can project nodes and links in the metagraph into hypervectors, like large bit vectors. Then you can do a number of search and manipulation operations in the hypervector embedding space. So I do think there will be a role for various kinds of specialized hardware, just like GPUs, which are these specialized matrix multipliers, have been super useful for deep neural nets. I would say also, though, you could do deep neural nets on CPU if you wanted to. I mean, it would be more expensive. There's enough money on the planet for it. The advance would have been slower if you had to spend that money. So in the same way, I mean, I think we can use Greg's row calculus stuff to boil down graph operations onto GPUs in a quite efficient way, going beyond what MapReduce can do. You still can't do as well there as you could do with dedicated hardware, right? And Roland compiling to the dedicated hardware. So I mean, that's exact amount of speed up on the algorithms we care about is to be discovered. I'm optimistic we can make a lot of progress even without custom hardware. But I mean, just like you saw with GPUs, like probably without custom hardware, we can do really cool things on a network of server farms. And if we want to put OpenCog Hyper on doing smart reasoning on your phone, you may need the special chips in your phone. That's sort of how I think it's going to go.
There's no concrete answer to this one, but I would like to hear your voice. You talk about using the Galois connections in order to improve the efficiency of the system and also to use Greg's work. But what magnitude of improvement will it get? You can choose like an example of implementation and like provide a factor of improvement.
Well, there's a lot of different things happening to try to make this system efficient, right? And so taking an algorithm and formulating it as a fold operation is one step. Then taking that fold operation, mapping it into Roland, which does its own rewriting to put it on the GPU, is its own step also. So I think each of those steps probably has a couple orders of magnitude improvement in it over what you would get if you were implementing in a very naive way and running on a single CPU processor. Because you can get a dramatic improvement by folding instead of implementing in a very naive, greedy algorithm way. And then with Greg's stuff, if you have 600 processors, you can get a speed up of that same magnitude. So I mean, we're looking at many orders of magnitude speed up, not just a small constant factor. There would be other ways to speed things up also. There's always many ways to speed things up, but I think we're in an interesting position here because we've been prototyping with these algorithms in OpenCog project for quite a long time. So we're hopefully not doing a lot of premature optimization because we've been, writing papers and doing simple, small scale experiments with these things. So we know at least the algorithms are somewhat useful for some things and not totally dumb. And now the question is, if you run it on shitloads of hardware and speed up by a few orders of magnitude, then what sort of magic happens? And I wish we had a theory to tell you what sort of magic would happen. We don't even have that theory for transformers, really. The study of scaling in these systems is mostly empirical, and we're sort of in the same position with what we're doing now. So how much speed up is one thing, but how much improvement of end user behavior do you get when you scale up to a certain level is a more important question, and we don't have a solid answer to that.
Thank you. I'm just going to ask one more quick question for a quick answer
okay.
from YouTube, please.
True or false question?
Yeah. Santa asks, well, it actually is a true or false question.
Santa Claus?
Yes, Santa, who's been asking some great questions.
I can't, if he won't give me any presents if I don't answer the way he wants.
It's yes, Santa.
All right.
As can node of a metagraph build in both symbolic and sub-symbolic integration, and the sub-symbolic part can handle a large amount of data.
you can so that's not a simple answer, but I'll try to keep it short. I mean, in the metagraph knowledge representation that we use in OpenCog, you certainly could represent any level of sub-symbolic data in there if you wanted to. I mean, you could represent individual pixels. You could make quantum truth values on your nodes and represent everything that happens in a bubble chamber if you wanted to. Now, as we've actually are working with it, when you have data that's, say, auditory or data that's visual, we found it just much simpler to process that data within a deep neural network. And then, say, each layer of the deep neural network, you put connections into the metagraph. And I mean, this kind of makes sense because, I mean, what comes out of the camera, it's a square grid, like it is a matrix, right? So then why not use a representation that is a series of matrices at various scales? So I guess the answer for now is you certainly could put all this into the metagraph. It's by far at the moment not the most efficient way to do it. So instead, we're working with neuro-symbolic systems where you take various deep or shallow neural networks and you tightly link them into the metagraph. That doesn't mean everything in the metagraph is symbolic in a cognitive sense, in the sense of like Peircean semiotics of manipulating symbols. Like you can do stuff that's very sub-symbolic using these nodes and links, in the sense that it has no clear symbolic reference. It's just a pattern that computes something from something else. But for dealing with large dimensional, like floating point matrix data, we're still tending to use neural nets and then link them into the atom space metagraph. What we're doing once we have our chip, who knows, right? I mean, to be discovered. Okay. But we should move on, I think.
Okay, thank you very much indeed, Ben. Right, next up, I'd like to introduce Peter Isaev, who's one of the, I hope I'm pronouncing that right, who's one of the organizing members of AGI-23 here. He's a PhD student in the Department of Computer and Information Sciences at Temple University, working with Professor Pei Wang, part of the Temple AGI team, which does research and experiments in the field of artificial general intelligence. And he's also one of the organizers of the NARS workshop. So please welcome Peter, who's going to talk about memory system and memory types for real-time reasoning systems. Thank you, Peter, and thank you for your patience.
That's fine. You're welcome. Can you hear? Okay. 1 second. Right. So thanks, everyone. Today, we'll try to talk about the memory for the reasoning systems. And I try to keep it short because we are already lagging behind. 1 second, I just remove that Zoom window out of the way. Just okay. So there are many desired capabilities for the AGI system we would like to have. And in particularly, AGI systems should efficiently process various types of knowledge. They should decide where to store this knowledge. They also have to know for how long it should be available. And they should efficiently retrieve it for inference, question answering, and goal processing. In particular, the real-time operation becomes a fundamental requirement when we're designing an AGI system, and especially when we're choosing a memory structure for it, because it has to support multiple memory types and efficiently process it into the constant time. Even though there are lots of rules to be applied, it's still going to be a large constant time of applying those rules. Here, we also need the resource allocation to integrate within the memory components. And that's required because we all know it doesn't matter how large the storage is, it's just a matter of time until it will be full or it reaches its full capacity. So in this discussion, we want to talk about the memory types in reference of NARS reasoning system. In particular, we want to show the memory structure and memory types used there. And because we strongly believe it will help others struggling in the same subjects, and that some of the problem will be transferable and highly relevant to the community and to development of the other AGI systems. Now, NARS reasoning system is basically a general purpose reasoning system proposed and firstly developed by the Dr. Wang. It operates under assumption of insufficient knowledge and resources, and it has a finite process demand. It's always open to accept any new knowledge during the runtime, and it operates in the real time, so it conforms to the real-time operation. NARS uses the non-axiomatic logic. Null logic is actually the logic we truly believe, the logic to go to deal with uncertainty. I will introduce some NARS consideration because it will be like a building blocks to proceed further understanding the memory types. Now, on the left, you can see the very high level implementation independent architecture of NARS. And you can see there is a red box. I would say it's an inference engine. So inference engine fetch some memory type, some memory items from the concept memory, then produce some derivation and either outputs to the environment or puts to some data structures or like component buffers or priority queue. And this is proprietary for the implementation. We're not discussing implementation here in detail. Something is mentioned in the paper, but here we try to stay away from it. So this is the cycle goes on and on forever until the reasoning continues. And the key things here is the memory in NARS is a concept-centric semantic memory structure in accordance with the null logic. So basically, it's a graph where the concepts are represented as nodes and links designate the relationship between them. Technically speaking, the memory is a collection of concepts representing a conceptual network with prioritized nodes and links. And here is important to introduce the budget. Budget is actually how important or importance of the data items to current context on the system. So budget is amount of system resources allocated to a specific item to allow priority-based selection. Budget actually summarizes multiple factors as taken into the consideration, including the urgency, salience of item, and its current relevance to the current experience of the system. So one of the key idea in NARS memory is the concept, the role of concept. So the concept is actually the major entity. It's an identifiable unit of systems experience that has a grounded meaning. So it also serves as a unit of storage that holds various components of knowledge. So as you can see it's here on the right, so this is the diagram of the concept, again, implementation independent, but we can see there the concept by default should have some data structure there to hold some information about knowledge. And it can serve as a blueprint for different other implementations. So it has definitely the links to other concepts and implementation specific. It can be different types of links. Because, for example, OpenRs and ONO, we have different links. It also have a declarative information storage, episodic information storage, and procedural informatic storage. Those are dedicated storages allow for efficient querying and processing during the reasoning cycle. So we can see that item distinction based on memory type already can be seen within the concept. So for example, procedural knowledge, which is in null, is a form of temporal implication, is typically stored in a specific table for faster inference within the concept. Now, episodic information is also present within the concept. It's basically present when events are being separated from the eternal beliefs. Now, in NARS, there are events and there are the beliefs. Events is basically information, it is a declarative knowledge with attached temporal information, episodic information, conceptually speaking, and the occurrence time. And the beliefs are semantic declarative knowledge, which has the declarative knowledge within structure of the terms, but it doesn't have any relevance to the temporal information. So basically no temporal information is provided. And also we can find some declarative distinguishing of the knowledge within the concept, on the concept level for eternal beliefs. So for example, we have the belief tables in OpenRs and as well as the ONA implementation. Now we can go ahead and actually classify and think and analyze the memory in terms of types as other AGI systems, as well as other cognitive systems like LiDAR, for example, that has multiple components and multiple memory types with the proprietary structures within it. So it happens that OpenRs has mostly all of the memory types, but the difference is that the memory system in NARS is unified and intertwined together to allow real-time and efficient reasoning. That's the huge distinction, actually. Now, we do have a declarative knowledge, of course, declarative memory in the NARS, and that basically contributes to the most content of the main memory. That is, the knowledge has been processed to become a concept nodes without episodic or procedural information. As a slide go back, so we can see here the buffers, for example, right? And we can assume there are lots of items, lots of knowledge is processed within the buffer. However, only some are being selected and make it the selection to the concept memory. So whatever have been selected to the concept memory and whatever does not have episodic or procedural information, it's supposed to be declarative knowledge in NARS, a declarative memory in NARS. And it turns to be like most of the memory is a declarative. Now, episodic is basically events or compound events, which is, again, a declarative knowledge with temporal information, which reach the selection to the main memory. And upon the perceiving of an event, its episodic information is stored locally to the concept level. Again, so we have some implementation-specific data structures and components where events, because they don't require shared term to proceed with reasoning. So we have some special components where we need to do some composition of the events, and sometimes there will be very many of those composition of the events, and only few can really survive to be selected from all of those components, buffers, and priority queues to make it to the memory selection, and then being transformed to the concept, and episodic information will be absorbed. So all of whatever is already absorbed in terms of declarative knowledge with temporal information, we consider to be in episodic. Now, procedural, it also exists in an OpenRs, and actually is a declarative knowledge, kind of declarative knowledge, which includes operation or compound operation within its description. Now, procedural information also is stored locally at the concept to allow efficient processing and efficient derivations. At the end, I will have a couple of examples that will be clear to illustrate how it actually works within the memory. So now we will try to do different classifications, like in terms of long and short term. It appears that technically we may be able to classify the memory in terms of long short term, in particularly that declarative information can be considered a kind of a long-term memory. However, declarative information can be removed from the memory by resource allocation. So there are possibly two scenarios. One is that the data structure is completely full. So what are you going to do? We just remove the whatever low important items for us. The second scenario is, for example, the importance or the budget of the certain data element has really decreased to the extent that it cannot actually compete for the resources because the importance is very low and system never selects that element and just stays in the memory for whatever until it's being overflowed. So in this case, so resource allocation can be seen as a decisive factor where to select a certain type of memory to be a long term or at the short term. Now, we also have two notions of memory in OpenRs. In NARS is working memory and attentional focus. So the working memory is the priority-based selection during the current cycle within the main memory and implementation-specific data structures. So what we currently selected from the concept memory and what we currently selected during this single reasoning cycle from all of the data structures within that concept, we consider this to be a working memory, because once we complete that cycle derivation, all the data items will be going back to their corresponding data structures, and their importance will be adjusted correspondingly based on the reasoning and based on the premises and how important they are. Also, the attentional focus is we could see it as a distribution of a higher priority within the priority-based data structures. So we can see it is that knowledge most likely be processed in the future unless derived or a new input task have a higher priority. So whatever higher priority or higher importance distribution within every data structure, we can see as attentional focus, because if something does not come up higher with more important than this, so system actually will keep that in its attentional focus until those importance is being lowered after the reasoning. Now I will show a couple of examples and we will understand how it works. So the first example actually introduces the simple problem of opening the door using a handle and knowing that the door is unlocked and knowing if the agent is in front of the door. So there are only there's only three inputs here and some system outputs. And the system is asked to derive the procedural knowledge, giving those input. So in the first and very beginning, it just says actually, if door is unlocked, if door is unlocked and something is in front, then using the handle they can open it. That's a piece of declarative knowledge. And right here we already have the embedded information of the episodic knowledge with in the form of temporal implication. Oh yeah, you can see it over there. And then you also can see here that's embedded in procedural information in case of the use operator or operation. So then we supply two events, which are declarative knowledge with the temporal information, basically an occurrence time. So we have the instance of door one is a door, and that's the same door one is actually unlocked. So we're just observing new instance of the door that's recognized to the system and to be unlocked. So those are the inputs. Now system outputs like the following. So we see that the door is become unlocked and it's the door. It's basically OpenRs using the compositional rules combines the previous inputs to create those derivations. So that's the first derivation. The second derivation, however, using deduction rule, OpenRs is able to derive the operation and actually open the door once it will be in the state of the, once it will be in front of the door, and once once using the handle to open it. Now it's interesting to see how all of those sorts of different types of knowledge interact within the same memory. That's what we see. What we say that the knowledge is intertwined within the same memory, and memory looks like a unique structure, a unified structure. So this is a memory fragment which is taken out of the reasoning cycle in the real time, and we can see that the red three nodes are actually corresponding to the inputs. So for the top input and the two events, those are the red nodes, right? Now, the orange node is actually the first derivation that NARS makes. Is a matter of composing those two input events into the one, right? So door is unlocked and the door. Now, the further derivation is made by the actually producing the procedural knowledge by opening the door with the use operation by using a handle. And we can see it there, the purple nodes. So we now derive that the door is in front. If a door is in front and the door is open over there, so that's the link. The red link is the representation of the visual representation for the procedural knowledge, such that we can use the handle to open the door. That's what it says. And now we can see, so all of the information, episodic, procedural, declarative, all of them present within this memory fragment. And yes, also the gray nodes is basically the terms, the composition into the concept, which are connected using the green links. And this might be implementation specific. Now, the second example I want to show is that just to illustrate that discussion about the long-term or short-term memory might not be very meaningful in the context of NARS. So the idea is the following. We try to learn the alphabet with the system. So basically, we try to input the letters to the NARS. And that's the pieces of the declarative knowledge. So we just have a list, have a long list of inputs. So we just say, is A is in letter, is B is in letter, C is a letter. So we're just providing that declarative knowledge, which is supposed to be a long-term memory. Now, somewhere in the middle, right, maybe, I don't know, in number 5 or 6 inputs. So we just submit an answer here, supply an answer here, meaning that are A and B also letters, right? So, I'm sorry, the question, not answer. So we submitting a question to the system and asking, are A and B also the letters, right? And system responds to us, yes, that A and B are the letters. So the frequency 1 and confidence 0.81. So very confident response. So yes, the derivation are registering. So new declarative knowledge is being produced, and it's again been stored. And we continue then to enter other input, like V is a letter, W is a letter, Z is a letter, etc. Now, whenever we entered all of the sequences of letters, not the sequence, all of the letters, including capital letters, we assume that the information is in the memory along with those derivation. And we now start to ask simple questions. For example, is A is a letter? And the answer is yes. B also yes. So all of the single letters looks like it remembers. However, when we now ask, are A and B are letters? So the answer is none. But wait a second, we just had it before, like, I don't know, 30 seconds ago. And then we ask another something like, are C and D are letters? And again, the answer is none. And it looks like actually the derivation has been made and it was registered with the memory, of course, and was living in the memory until the data structure became overflow, and it has to be kicked out due to low priority, due to low importance of these data elements to the NARS. However, if we ask for some sequences of letters which corresponds to the last inputs, like T, U, V, W, or X, Z, it remembers because it's still most recently used, and it still thinks of them as an important concept at this current stage. So now I think we almost reached the time limit. So I will just go over the takeaway here. And the takeaway is the following, is that OpenNARS or NARS has the unified structure, allowing the same piece of knowledge to contain declarative, episodic, and procedural components within it for efficient processing. And different forms of knowledge actually are interacting and being processed within the same memory during the inference process. Now, NARS does not include the well-defined separate components dedicated for different processing type, but it features its own integrated approach to memory, and that that long and short-term memory classification actually might not be very meaningful whenever we talk about the NARS and its classification by the duration. I think I will stop here. Thank you very much.
That was fantastic. Thank you very much, Peter.
Sure.
Janet had to step out for a bit, so I am the Janet right now. Any questions from the room?
Is there any benchmark available, like number of concepts that it can process and how fast?
There have been, but I don't remember now from top of my head. Yes. Yes. We can probably take a look later. Yeah. And it's also implementation specific now. So different implementation gives a different results. But yes, good question. Thank you.
I really enjoyed the breakdown of the declarative, procedural, and episodic knowledge. Have you tried putting NARS in the cloud? Have you done any runs with
Not at the moment.
The cloud system?
Not at the moment.
Okay.
Questions? All right, fantastic. Thank you so much. That
Thank
was
you.
wonderful.
Thank you.
And it's my great pleasure to present Selmer Bringsjord. Hope I got that right. Who's been asking fantastic questions and obviously very familiar up here. The mu cognitive, did I get that right? Mu cognitive, correct?
Yes, approximately anyway.
Approximately. Meta architecture as touchstone for standard modeling of AGI level minds.
Probably a second grader could do that. Yeah, that goes here. Okay. Are we working? No, we're not. Interesting. Let's try. So we don't care about the title slide. Yeah, two of us are doing corporate stuff. We don't care about that. Actually, it's Ben who brought me to this point years ago in saying, I do agree that you should follow me in looking at academic education and the role of that in AGI. It was his idea, and I'm trying to do it. The last keynote related to this. That's my kindergarten, still there, founded in 1936. So I'm really talking about the grade progression. This meta architecture, though, goes past grade 16. So you have to go to school for quite a while. And you did, so you're in luck. You'll be able to understand. There's the magical, apparently, second grade. Yeah, I could have gotten all those problems that were shown 100% correct quickly. And then my mother would have said, that's not that great. You need to show me the proofs, and I would have shown her the proofs. So there are a lot of cognitive architectures out there. I don't know, 75 is conservative. So I'm showing a breakdown that I got courtesy of one of my grad students, who's also a NARS expert. Fortunately, I don't know, say there are 75. So what I'm trying to do is figure out if there's a way to standardize them somehow formally. I really don't care per se about human cognition specifically, but it's got to be human level, could be alien, could be above human level, it doesn't matter. I don't know for sure if all these are geared to some particular level. I don't think so, but that's the idea. So if there's a capital X appearing as a variable, it refers to any cognitive architecture, okay? The subscript on it depends. And this is the foundation for the whole thing. It's actually a relatively simple idea. What we want to do is take, here it is annotated. We want to take the kind of natural language sentences that have been uttered by the smartest humans since at least Euclid, and come up with the definitive formal expression of those first. So here I'm just going with 2 + 2 = 4. That's the SA. The A is an agent. So that's just a set constant, if you will. And then I will just tell you that the mu cognitive architecture has the classic and indisputable gold standard formalization for what that means when some agent believes that 2 + 2 = 4. Now you could say, well, I'm prepared to throw away all of formal science. That wouldn't be good. Mu is not a candidate in the race or the competition of what you saw earlier in those 75 plus architectures. Mu is based on what we cannot give up. We might be able to give up sort of, you know, some aspects of quantum mechanics. We're not giving up Peano arithmetic, okay? And so this doesn't even have quantifiers in it. That's what we start with. So we've got this biconditional as a given, and then we have the goal for any cognitive architecture that wants to measure up of establishing, or having someone else perhaps establish that biconditional, that statement that some agent believes that 2 + 2 = 4 holds if and only if something happens and is represented in the cognitive architecture in question. But the trick is, the challenge specifically is that we have to prove 2 up there. If we have the given plus 2, then we can prove that standardization has been achieved. Okay, so this is the basic idea, starting simply. All right, so in the paper, we describe 2 pretty much expected success stories, and they are SNEPs and NARs. So I can't say for sure that the proofs in the case of these theorems are formally verified, but I would come close to staking my life on this. All right. And then it's been pointed out to me before the paper came out and we circulated it, Selmer, you actually claimed in the literature that Clarion could do this. And you're supposed to know that John Anderson, in the case of ACTAR, once upon a time, many decades ago, actually said that first order logic was the basis for the declarative side of ACTAR. So you should probably say that those achieve standardization of the level of 2 + 2 = 4. So I'm going to put check marks there. Now, yes, I couldn't resist. If we move outside the category officially of cognitive architectures, what happens with GPT-4? We just set it to one of the cognitive architectures, and then very much connected to the first keynote talk today. Then we go to Peano arithmetic. So we want to go to the theory that is produced by Peano arithmetic, which after all is just an axiom system. I should just skip these because there's absolutely no surprise here, you know, right? So it's total, absolute, undiluted incompetence. So the simplest theorems of elementary algebra. So here's an example. You know, is it true that there is an X which is such that if it's a prime number, then everything is a prime number? And, you know, this actually is an interesting theorem in algebra because this is not a matter of calculation. And I'm not sure there's a lot in the data set, but there are an infinite number of these kinds of theorems that don't relate in principle, I don't think, I mean, my guess is to any of the data, but you sure as heck better be able to see and prove that these are correct. It strikes out. And we've done this quantifier complexity of this. I mentioned in my rejoinder to your rejoinder, you know, there's only 2 quantifiers here, folks. But okay, so it's a strikeout for GPT-4 treated hypothetically as a cognitive architecture. The M here is by definition, so that green check does not earn me any kudos. But we've expanded the list a little bit. Now, let's go to the second order case, second order Peano arithmetic, which basically means, for those of you who are unfamiliar with it, we turn the technique of induction, mathematical induction, into a formula itself, and then we start instantiating in that formula. In truth, and I look forward perhaps to talking to Noah about this at some point. In truth, if you've paid attention and know a thing or two about logic, you've already seen that I'm not using fixed Peano arithmetic. I'm using meta Peano arithmetic because I'm using formulae that are templates for instantiation, okay, and when instantiated, produce perhaps a theorem of piano arithmetic. So GPT-4 or any large language model really has, maybe it's possible. I think when we determine the expressivity of these systems to a greater extent, we'll see that it's mathematically impossible. Because if you can use meta logic and reason at the metalogical level, which we have to do, okay, all of that by definition is going to be continuously novel in human dialectic. So I don't know how data sets are going to help you, but maybe someone will figure it out. So here's PA3, which I was playing around with over there. So I threw this in because third order logic, you know, people have the idea, well, third order logic is very exotic. This is different than higher order logic. I just want to be clear. The higher order logic community says, look, you're going to run out of symbols, so let's start talking about higher order logic. This isn't what I'm doing. I'm channeling Kurt Gödel, who said, you know, humans use third order logic routinely. So my example here, suppose there are properties canines, assertion, Buford don't share, and that some of these unshared properties have the property of being scary. So in third order logic, you can allow properties to have properties, which again, we do. Given this, is it true, et cetera, and it's of course going to fail. So, you know, I wrote out on the paper what it would look like in third order logic. That was an interesting effect there. And, you know, it's really simple and people can understand this. I don't know about second graders, but I'm pretty sure grade school kids could understand this. It has no clue. And I came up with a scenario that actually satisfies the identity of our two dogs. Okay, there's the dog. One person calls the dog by one name, another person calls the dog by another name. It's the very same frickin' dog, and it ain't a tiger, and a tiger is a scary property. You know, this is not rocket science, okay? Sorry, I don't know how this is going to work for the LLM people. Put logic in control of cognition, which is what happens when you're a rational cognizer, and then use these other things as subsidiary, less reliable techniques. So now what about second order logic in connection with the paper and the assessment of these architectures? So this does get very interesting. I have no idea how this is going to work out when evaluating these architectures. I think most of them are going to strike out. So here's a simple Leibnizian theorem going back to Leibniz, right? So if it's the case that there's a property that A has and B does not, then we know they're distinct. Well, we could argue about whether this holds in all physical scenarios, but you know, this is a theorem in second order logic. So, well, you know what's coming. I ran this by GPT-4, and you know it's verbose, and the language conforms, I think, formally to Frankfurt's book called Bullshit, which I recommend. People often ask me, how would you classify what? You know, I would classify it by just citing the book because it's confident. And if it really had the objective of persuading you like a sophist, it would be wonderful, you know, but it's basically total bullshit. And the conclusion here, we're talking binary, you know, this is like binary logic, elementary. So it says no, you know, they're not distinct, you know, they're actually the same. How easy is it for modern automated reasoners to get this? Well, there aren't that many automated second order reasoners, but not hard. So we don't need to look at the proof here. This is a hypergraph, not a metagraph. All right, so now things are going to get really interesting in a scorecard for these cognitive architectures. ACTAR is not going to work. because if Akhtar's commitment decades ago, courtesy of John Anderson, is still in force, it's going to be a strikeout. Okay, so I lost one. You know, ClarioNet, I don't really know for sure. Clarion's weird because, you know, Ron's son was always committed to symbolic, sub-symbolic. And on today's AI scene, it's an interesting architecture. So I don't know. I don't know about SNEPs, and I really don't know about NARS. Now, Pei's here, so I look forward to talking to him. If we don't finish the conversation, it'll be, you know, it looks to me like it's not quantifier rich, and we've got to get to second order quantifiers. As you saw earlier, there's an existential quantifier for a property variable. GPT-4 or any such thing, of course, that's a strikeout. But that's, again, not anything that's praiseworthy. That's by definition. I'm not inventing anything here. Okay, I'm not doing anything really creative. I'm just saying, for God's sake, since Euclid, we built up the formal sciences. I'm just looking at arithmetic. If you want, this is just number theory. We got number theory, topology, geometry, algebra. We go through it, and then we're going to have physics. Now, on this issue, aliens versus natural, I tend to think that the progression that our version of human persons, we're persons, but we're the human variety, we've been on this track of going from elementary arithmetic in the bullseye there, baby arithmetic, we made it to piano arithmetic, second order piano arithmetic, and then at the outer level there, we have the Gödelian results, essentially. So I think every creature that's really smart, that reaches AGI and beyond, is going to be on this track. If the aliens aren't that far along, they'll be further back. They're going to need to count things. They're going to need to do arithmetic, and they're just going to follow the track. And then I have, well, I won't bother with that. So, but stop here.
That's wonderful. Thank you very much. Questions from the room? All right.
Peter Voss mentioned in a talk yesterday a system, a Helen Hawking type of system, where it doesn't really take sensory input from the world, but moreover just does reasoning. So is this system, the Mu system, more of a reasoning system, or is it, do you conceive of it taking information, sensory information from the outside world and then building up its own internal representation?
Yeah, no, great question, Michael. The answer is it doesn't take any information in from the outside world, except at this point for what, again, is invulnerable. That is, it's got number theory. It's got elementary algebra. That's all I'm using here. But my assumption is that these creatures, whether they're on Earth or another planet, have to minimally basically do two things. They have to develop mathematics. They have to connect the mathematics to the physical world and how things move in it. So the next thing would be to go to physics. But physics, as has been formally captured, and we have axiom systems for that, special, quantum, and the classical mechanics case. So there wouldn't be perception of the outside world, as it happened in the case of humans building up these theories through millennia, really. It would be the fruit of that effort that now is incredibly, well, maybe not relative to some Martians or something that are super into, but mature. So no, but in my AI work, that's not what, but in my AI work, of course, so you have to have perception. And if you looked at the brilliant second grader, okay, take away the eyes and take away manipulative ability, and I guess the second grader is kind of dead. That may be part of what you're getting at. Yeah.
So yes, so so some of these models are pretty good at automating some of the higher order logic theorem proving and so on. But I'm offering a truce now.
Okay.
Which is tool usage. So one of the things that GPT-4 does very well is to call a tool. So for example, if it cannot do, determine whether or not an integer is a prime, it actually creates a Java program, which will test for primality, and then it'll run the Java program and give you the results and say, okay, it's a prime or not, and based on the tool. So what if we actually take your cognitive architectures, whatever tool, the tool of your choice,
right,
and then plug it into GPT-4, and then for such problems, it's going to give you perfect answers, but because it'll use M.
Yeah, well, if I was running a for-profit corporation that had any degree of dependency on a large language model, I would have, before disclosure to the general population, have already had my smartest people working on treating these things as no more than glue, because that's really what's happening. Okay, it's not, of course, directly to my talk. Now, but as I said along the course of this presentation earlier, what we should have done was put the rational side of cognition, and maybe there's still a chance, in control, okay? And what we glue to it would be things like what these LLMs can do. Instead, we have crazy people, okay, most of whom will simply not debate me. Okay, I would have bet $1 million. Okay, I'll have one logic problem, generally of the ilk that we saw here, and bring in someone who's an end-to-end large language model person, an end-to-end deep learning. So I mean, we were in disagreement before. I'm in agreement with you. That's obviously what we got to do in general. Now, the end-to-end maniacs, it's just not gonna work. It's just, but yeah. So, well, hopefully.
We'll take one more.
Hopefully, yeah.
Thank you for your speech. I have a question about after regressive models in general.
Yeah.
There is AlphaFold and AlphaFold 2 systems, which is in general after encoders systems, which helps to solve protein folding problem. Before any other approaches tried to solve this problem, and it was hopeless.
Okay.
And this problem is a geometric computations, I would say. So it looks like after encoder model can capture, underline the structure and produce good enough results. And can you what do you think about the ability of attention-based after encoder models capture very sophisticated, complex underlying geometric structures and produce high-quality results?
I didn't hear the example of the great solution that happened. Was that protein folding? Or?
Yes.
Protein folding. Well, I'm ignorant. I don't know. Okay, I have a scientific American understanding, which is pretty much worthless scientifically, of protein folding. I don't know how hard it is in terms of computational complexity, or in terms of solvability and relative solvability. I just don't know. So I don't know what to say about it. But my firm intuition is that it's merely calculation. If it really was some groundbreaking thing that happened, it's probably just calculation beyond the capacity, at least up till that point, of what humans could accomplish. What I'm talking about are formal systems and formal capacity that is not calculation. Once we have it, we could do some calculation, but you generally don't get a Fields medal, right, which is relevant to for doing something calculative. You get it for doing something creative, but still probably within the bounds of third order logic in some branch of mathematics. So sorry to disappoint you about the lack of specifics. Yeah.
That's great. Thank you very much, Selmer.
Yep. This goes back to, said it, okay.
And next we have Sergey Shumsky, virtually, I believe. I haven't seen anybody of that name volunteering to come up yet. Presenting on ADAM, Adam, a prototype for hierarchical neuro-symbolic AGI. So welcome, Sergey.
Thank you. Do you hear me well? Yes.
Yes, sounds great.
Okay, I'm sharing. Okay. Let's start.
Went on mute. We didn't get to hear your presentation. Can you hear us?
Yes, do you hear me now?
Now we do, yes.
Okay, sorry. So I'm introducing myself. So I'm head of a cognitive architecture lab in Moscow Institute of Physics and Technology, and I'll present the hierarchical neuro-symbolic architecture, deep control, its working prototype, ADAM, and some results of experiments. And to start with, the agent's behavior is governed by some rules of thought, which we call logic, and it defines the dynamics of mental states, which can be divided in two stages, action and perception. First comes action selection, which can be thought of as a prediction of a next mental state, since the agent don't know his next sensory value. And the perception of this sensory data leads to the state transition to the next mental state and the evaluation of this new mental state using some reward function, internal or external. As a team from DeepMind stated in 2021, reward is enough for learning goal-directed behavior, that is to infer logic through reinforcement learning. In reinforcement learning, the intelligent decisions are based on a value function Q, which is sum of expected rewards over some planning horizon, and the larger this planning horizon, the stronger the intelligence. The good news is that there are well-known algorithms such as Q-learning to iteratively learn the value of all the mental states and the transition dynamics. And these two functions define the mental logic of the agent. That is what is called in reinforcement learning the strategy. The bad news is that the complexity of Q-learning scales as the planning horizon cubed. That is, long-term planning requires so many iterations that it makes the strong intelligence almost unattainable. And the solution we propose is to implement hierarchical thinking. That is where several layers they produce short-term plans which are easy to learn, but each on its own timeline. And the resulting planning horizon, and since the intelligence grows exponentially with the number of the layers. To illustrate the main idea of our approach, we consider the reinforcement learning as learning some mental language. And the formal language is defined by a finite set of its characters on alphabet and a set of rules for constructing all valid strings from those characters. In our case, the alphabet is represent the set of all elementary actions, and the vocabulary of the mental language are the all most frequently used combinations of those actions found in Q-learning. We can construct this vocabulary by using empirical counts of the pairs of mental states while learning the transition function. When this empirical count for some pair of mental states exceeds a predefined threshold, we define a new word of mental state as the combinations. The result of such learning is a nested set of grammar rules for constructing the complex plans from individual actions using the agent's mental logic. Moreover, we can define the semantics of this language using the statistics of right and left contexts of each mental state. These semantic vectors are well known in natural language processing. We can then cluster all these semantic vectors to find synonymic groups of words which has similar meaning, that is used interchangeable in similar contexts. And these clusters can be thought of as symbols of a new language, a meta language, defined on a larger time scale. And this meta language then can learn its own grammar, logic, and semantics, and so on. And thus we can construct a whole hierarchy of mental languages. And the result is the hierarchical architecture, which we dubbed deep control. It differs from traditional deep reinforcement learning, where deep neural networks are used to implement the value function to make separate decisions. On the contrary, in deep control finds a set of nested plans on the corresponding time scales. And in a sense, both architectures use a kind of deep learning, but traditional deep learning uses a stack of simple mappings in neural networks to define an arbitrary mapping. And in our case, in deep control, we use a stack of simple controllers to define an arbitrary controller. We developed a prototype of this deep control architecture called ADAM, In Adam, all the layers are similar and consist of several main components, the 4 of them. The encoder translates the semantic vectors of the previous layer to the symbols of the current layer, parses, then combines these symbols to words of the current layer. Planner predicts the next word to choose the best possible implementation of a higher level plan, and the decoder translates this plan to the layer below as a list of all its possible implementations using episodic memory. We used Adam, for example, to train a robotic arm to reach an arbitrary position here. Here is a corresponding learning curve, and this is a simple task. This is actually it is a single layer model, and now we are working on more interesting and prospective task. This is a conversational intelligence. And contrary to transformer language models, which generate text word by word, Adam constructs his utterances many words ahead, combining the whole sentences. And this graph shows the perplexity as a function of the number of layers. And as you see, the more layers, the better the quality of text generation. And saturation here is due to the lack of data in this concrete experiment. What is important is that the complexity of learning of our model is proportional to the data size, and is orders of magnitude less than that of neural networks, which are quadratic. Summing up, we propose a hierarchical neuro-symbolic AGI architecture capable of automatic generation of optimal rules of behavior, which can be interpreted and debugged, and with the planning horizon, which increases exponentially with the number of layers and with the linear complexity of learning. So that's it. Thank you. Thank you for your attention.
It was great, Sergey. Thank you very much. Any questions from the room? All right.
Hi, thank you very much. 2 questions. One question, I didn't see a component that verified the predictions. So the system makes predictions. The predictions are captured in the hierarchy that's constructed. But then is there an element or a component that actually verifies the predictions? And if so, which one is that? That's the first question. And then the second question was the reward. Is there an intrinsic reward? I'm assuming that there's no extrinsic reward, but is there an intrinsic reward, and is the reward computed by the successful prediction? Like if you make a prediction that's successful, you have reward, and if you don't, you have correction or punishment?
Actually, currently we use reinforcement learning, which is based on the external reward, based on the task at hand. But you are right, in minimal free energy principle, there is an internal reward. And we are going to implement this one too. It fits this architecture well. And as for the first question, you see, we have prediction based on the learned value function and based on the transition function. And this prediction helps us to choose the best implementation of each step. So each step of the higher order plan has a set of implementations, and these implementations they are known for this layer due to episodic memory, and from these implementations, the layer chooses the best one according to its logic and according to the current context, which is given by a current mental state at this level. So each level has its own logic, and it implements the knowledge of this level to choose the corresponding plan implementation at this time scale, at the scale of this level. And then symbol by symbol, it translates this plan to the lower level. And the lower level finds the implementation of those steps based on its own knowledge, lower level knowledge, I mean.
Thank you. Any other questions? All right, wonderful. Thank you very much, Sergey.
Thank you.
Next, we'll go virtually again to Paul Rosenbloom. So rethinking the physical symbol systems of hypothesis. Dora's obviously very excited about these presentations. They're very good this afternoon. So this will be our final presentation before we'll have a quick break. We've got 4 more papers to wrap up the day and the AGI business meeting for those interested in attending, and then the banquet this evening. So last paper of this session before the break. And welcome, Paul.
Okay, thank you. So this is a key hypothesis that's been around in AI for over 50 years. It's been questioned repeatedly and insistently, but never been truly replaced. So let's start by reviewing essentially the physical symbol systems and then the hypothesis and move on from there. So physical symbol systems, as they're originally conceived, symbols are distinct patterns in the physical world. They're natural, that is, they obey the laws of physics and are amenable to engineering. And they're not limited to what is in human minds, though they were inspired by how humans use symbols. Symbols can be composed into symbol structures, also known as expressions, and processes can create, modify, reproduce, and destroy them. An expression designates an entity if its use depends on the entity's nature. This can be for internal as well as external entities. And for external entities, it provides one aspect of grounding in terms of relating, relating what's inside the system to what's outside the system. An expression is interpreted if it designates an internal procedure for execution that then is executed. This can be considered as a form of procedural designation. Physical symbol systems provide a form of universal computation. So they're Turing equivalent and essentially the equivalent to modern digital computers in terms of their abstract ability to compute. So the hypothesis, how this goes back to Newell and Simon, a physical symbol system has the necessary and sufficient means for general intelligent action. This is an empirical generalization rather than a theorem. And they provided both sufficiency and necessity arguments for this, again, not a theorem. So the sufficiency argument was based on 2 aspects. One is the universality. It says, assuming intelligence is computational, then universality should provide sufficiency. But it also argued based on the success of symbolic systems to date, that meant as of kind of the 1970s. The necessity argument said humans appear to be such systems, So that means in some sense that it seems like they must be necessary. And the lack of alternative approaches that were nearly successful, at least as of that date. And that included neural network systems, at least as of that time. There's a couple of key quotes from Newell in 1980, kind of suggesting how important, at least he felt, this hypothesis was for the field. So the first one, in my own view, this hypothesis sets the terms on which we search for a scientific theory of the mind. And the second one even goes further. The physical symbol system is to our enterprise, but the theory of evolution is to all biology, the cell doctrine to cellular biology, the notion of germs to the scientific concept of disease, and the notion of tectonic plates to structural geology, basically claiming it's the foundational theory out of which all AI or AGI should grow. But there have been a number of critiques over the years. Here are four that Nielsen summarized in 2007, along with his particular responses to them. So the lack of embodiment or grounding, he felt this was just incorrect, misunderstanding what already provided. You can see what I've already said in terms of at least one form of grounding. There are other forms that have to do with essentially the role of perception and action play in grounding internal symbols in the external world. The need for non-symbolic or analog processing. He agreed with this complaint and basically said, well, take a simple system, let's add numbers to it. And he, in fact, provided one early form of hybrid that did this. Brain style versus computation style, that is the notion that brains aren't computers. The argument here is that brains are, in fact, computational, particular sort, even if they don't look like traditional computers. And the last one is kind of an odd one, the mindlessness of much of what appears to be intelligent behavior. The response he had was essentially mindless constructs will yield mindless behavior. The obvious implication of that is that to have true minds, you have to have more than just this, or more than just the mindlessness behavior. There are at least two lingering critiques that are highlighted by the recent successes of neural networks. And I've categorized them. One is a sufficiency challenge, one is a necessity challenge. The sufficiency challenge is essentially the lack of numeric processing that Nielsen identified. And when we look at sufficiency, you can look at the fact that numeric processing, at least in neural networks, can now do better on many problems, weakening the argument from successive symbolic systems. You might also point to graphical models and probabilistic programming as further examples of this weakening. Universality still supports sufficiency and implies you can do numeric processing even if you start with just symbolic, but this is weaker than the combined argument that was originally made. In fact, it gets even weaker when you look at the notion of cognitive architectures and how, if you, for example, look at the common model of cognition, it argues that numeric processing is required at the same time scale as symbolic processing. Therefore, you can't just start with the universal symbolic reasoner and build numeric processing on top of it. You can do that, but it's not sufficient for building cognition in terms of a cognitive architecture. The necessity challenge is more directly derives from neural networks. Humans also appear to be such systems, so it's not just an argument for symbolic structure systems from human minds and brains. And in fact, they provide an alternative that works as well or better on many problems than pure symbol systems. So the latter part may raise this question, should there be a neural network systems hypothesis that replaces the physical symbol systems hypothesis? I've just commented here shortly on the sufficiency side of this. So we know the neural networks have shown a remarkably wide range of successes recently. Some have even been shown to be universal. But many include, the more complex ones in particular, include explicit forms of symbol processing. So systems like AlphaGo and AlphaZero that play board games have added state space search on top of the neural networks. And that is essentially a form of symbolic processing. LLMs clearly operate on word sequences, again, a form of symbolic reasoning. And there are various forms of composition that are common in neural networks. There's also the contentious question of whether all neural networks involve symbols of some sort, whether the advocates of the technology want to agree to that or not. So to me, this question remains open. So an alternative is to consider a particular form of hybrid symbol system along the lines that Nielsen has suggested, but somewhat different, that subsumes both physical symbol systems and neural networks. That's essentially the line that's pursued in this paper. So we're going to go into a hybrid symbol system that's inspired by the common model of cognition, which is an attempt to understand at an abstract level what's minimally necessary in a cognitive architecture to achieve human-like, not quite human level, but human-like cognition. And also by the Sigma cognitive architecture, you can view that as essentially a spin-off of SOAR that I worked on for roughly a decade. So we're going to start by stripping the notion of a computational symbol. This is in symbols in general, but specifically a computational symbol, down into a non-obvious essence. In particular, it's going to be an atom, or we can think of it as a placeholder in kind of a Drew McDermott fashion, that is indecomposable in other atoms and distinct from all others. Okay, so we're saying that's what a symbol is. So in particular, issues of designation and representation, which are thought of as central to at least human symbols, are not part of this essence. So it differs from this notion of human symbols. It also differs from Nielsen's suggestion of just adding numbers onto existing symbol systems, which all assume designation as one of the essential attributes of symbols. So capabilities such as composability, designation, and interpretability, which you can think of as procedural designation, all become optional. So you can get a hierarchy of optional characteristics that exist somewhat like this, with interpretation here and declarative designation in terms of both internal and external. All of these exist, but only now on a symbols by symbol basis, and some but not all such systems are universal. We can also then add the option for quantitative metadata on top of symbols and expressions, which you can think of as data. This is along the lines of what the common model has hypothesized. And then clearly see that physical symbol systems are clearly one special case, where everything, at least except for the hybrid, is essentially required for all symbols. The claim here is that neural networks are another special case. That is, they are examples of hybrid systems of this sort, rather than just being combined at a gross level, as in, for example, Clarion, where you have a symbol system and you have a neural system, and together they form a hybrid system. So let's look at how neural networks are hybrid symbol systems of this particular sort. So let's start by considering a small feed-forward network for paired associates, that is, relates words to words, as you might see in simple traditional psychological experiments. The nodes in the input layer are hybrid symbols that do not designate. They're hybrid symbols. They're placeholders, essentially, or atoms that have numbers associated with them. That makes them hybrid symbols. They're neither subsymbolic nor microfeatures in kind of the traditional distributed neural network interpretation. So the individual elements are hybrid symbols in this way of thinking about things. Composability of a very limited sort yields the input vector. So it's a vector which is composed of hybrid symbols. And it designates the word expression on the input. So that's a relationship from this hybrid expression or hybrid symbol structure to another symbol structure which represents the word. The nodes in this word expression externally designate letters. So here we get to external designation or grounding. And in fact, the entire word structure, you could say, designates Alan Newell. Now we get to procedural designation or interpretability. So internal and output nodes all designate procedurally. That is, they designate a procedure which is the combination of summation and nonlinear transformation. That's essentially what happens at nodes in these kind of feed-forward neural networks. Links themselves also designate procedurally. They are expressions that combine two nodes and have a number associated with them, which is a weight. And then they designate the product of the node activation with the link weight. Okay, so that's the notion of a particular form of hybrid symbol system. There are, of course, many varieties of hybrid symbol systems out there. This is one particular version. So what kind of hybrid symbol system is this neural network? See, we got two W's there. It provides limited forms of declarative designation as the input node. The input nodes, as we saw on the previous slide. It provides quite a bit of procedural designation or interpretation at both internal and output nodes. Also actually at the links, and provides restricted forms of composition via vectors at the levels and links across the levels. If you look further in the neural network literature, you can see them going significantly beyond this in various ways, adding additional forms of declarative designation for some of them, adding additional forms of compositionality. You can, for example, look at convolutions, you can look at graph neural networks. They're all additional forms of compositionality in neural networks. And some of them add in universality. Okay, so what I'm proposing is a hybrid symbol systems hypothesis, or HSSH, in the form of hybrid symbol systems are necessary and sufficient for general intelligent action. So you can see it's aligned quite strongly with how the physical symbol systems hypothesis is expressed. And it's being proposed as a replacement for the PSSH. It's still an empirical generalization, not a theorem. And again, there's a sufficiency argument and a necessity argument. The sufficiency argument retains the possibility of universality from the PSSH, and it can appeal to the successes of symbolic, numeric, and hybrid systems. So there's a much broader base of success in this sense. The necessity argument co-opts the existing human cases, what we've seen for both symbol systems and neural system, and the range of successes listed above for sufficiency. That is this kind of thing. And it raises the question, are there in fact any possible alternatives? For example, quantum or other kinds of things. But that's the general idea. Conclusion. So we're getting there quickly. We've stripped down the notion of a computational system to an atom or placeholder, where all the other aspects that are normally thought of as part of a traditional physical symbol system now become options. Added in the notion for quantitative metadata on these symbols to yield hybrid symbol systems, and showed that simple neural networks are instances of such systems. The assumption is that more complex ones, which are all basically variations on these simple ones, or at least most of them are also instances of such systems. And then propose this as a replacement for the physical system, simple systems hypothesis. There's a separate hybrid hypothesis in the paper for cognitive architectures. As discussed, numeric processing is concluded to occur at the same time scale as symbolic processing. So the argument from universality of the physical symbol system doesn't work here. And that's it. Questions?